A study of the hardening of steel shows that steel can be hardened by heating and quenching. Hardness, however, is only one of the useful properties of steel. Toughness, for example, is frequently essential. But fully hardened steel is not tough. On the contrary, it is usually brittle. Some steel parts, like this ball bearing, call for high hardness to resist abrasion, while only a moderate degree of toughness is needed. Other steel parts, like this automobile spring, require toughness to resist impact or shock, but also must be hard for resiliency. These gun parts, called front guides, have been fully quench hardened. The steel is quite brittle. It lacks toughness. To make this type of steel tough enough for service conditions, it is tempered. Tempering, or drawing as the process is also called, is a method of toughening steel after it has been hardened. In the toughening process, the hardness is reduced. When we speak of toughness, we need a quantitative guide, an accurate means of measuring it. The Charpy impact toughness testing machine answers that need. It determines the resistance to impact offered this pendulum by a specially prepared specimen bar of the steel under test. The specimen is placed across the pendulum's line of travel. The pendulum is drawn back to a fixed angle. When the pendulum is released, the energy required to break the specimen reduces the swing of the pendulum. This dial registers the pendulum's travel. It measures in foot-pounds the energy required to break the test piece. This is a measurement of the steel's toughness. When previously hardened steel parts are to be toughened by tempering, they are first reheated. Tempering temperatures are below the steel's lower critical temperature, the temperature at which the steel first began to harden. The parts are kept in the furnace until they are uniformly heated. Thus, tempering time depends on the thickness of the pieces and the temperature to which they must be brought. After heating, the parts are removed from the furnace and allowed to cool in air. What has happened in this process to change the properties of the steel? Here are 5 micrographs of an SAE 1043 steel, which show its structure after tempering at progressively higher temperatures. In each stage pictured here, the steel is tougher than in the previous one. The first micrograph is of the fully hardened steel. It shows the typical martensitic structure of plain carbon steel at maximum hardness. The steel's Rockwell C reading, the measurement of its hardness, is very high, 60. On the other hand, its Charpy reading, the measurement of its toughness, is very low, 3. After tempering at 400 degrees Fahrenheit, only a very slight change in structure has taken place. It is still essentially martensitic. Point 2, and by its Rockwell C reading, which is down 4 points to 56. When the steel has been tempered at a higher temperature, 650 degrees, a recognizable change can be seen in the structure. The carbide has started to precipitate from the martensite. The carbide appears black in the micrograph. The toughness, however, has barely changed. It is now at 6.3, even though the hardness has decreased to 49. It is necessary to go to higher temperatures to obtain marked toughening. Tempering at 900 degrees produces a further precipitation of carbide from the martensite. These carbide particles, diffused in the martensitic structure, are beginning to coalesce. Now the steel's toughness has jumped to 22. Its hardness is down to 39. This micrograph shows the steel after tempering at 1275 degrees, a heat closely approaching its lower critical temperature. A definite coalescence of the carbide particles has taken place. This is discernible where the black lines have broken up into dots. The steel is now very tough. Its Charpy reading is 65, but it is quite soft. Its Rockwell C is 20. From these and additional test data, a graph can be made to illustrate the relation between the toughening of the steel and the accompanying change in its hardness. As abscissa, we have the tempering temperatures in degrees Fahrenheit. As ordinates, we have the Charpy impact toughness in foot-pounds. We plot the values obtained by testing our steel after tempering at progressively higher temperatures. These points give us this curve. Now we also plot as ordinates the hardness readings of the steel at the same tempering stages and obtain this curve. We can see that there is a generally consistent relationship whereby hardness decreases as toughness increases. But there is an exception to this rule. Between 450 and 650 degrees, toughness actually decreases a little. However, there is no corresponding deflection in the hardness curve. This is called the brittle tempering range. But at temperatures above this range, and particularly beyond 800 degrees, the toughness increases very markedly. The same graph, drawn for any other plain carbon steel, would show a similar relationship between toughness and hardness.
This video is going to look at C.1.6, describe the effects of heat treatment in steel. So basically, once we're started to create the steel, we want to be able to manipulate the steel to suit the purpose. So for example, steel in a car may not be exactly the same or need the exact same properties as steel in a building. So heat treatment is the way that we actually alter the size, arrangement, and interaction of the grain structures that make up metals and alloys. So what does that mean? Well, if you zoom in on a metal or an alloy, what you see are these grains. And these grains are basically sort of sections of atoms that have lined up in the same crystal, they have the same alignment, and then another grain has a slightly different one, slightly different one, slightly different one. And that's beneficial to us through heat treatment. We introduce this and change it. And that's beneficial because if we had just a perfect metal where everything lined up, it's not as strong, because if everything lined up perfectly, it would kind of be like a stack of paper, and you know how you can easily slide one piece of paper off the top because it all lines up very easily. So they could just slide by each other. Your metal would not actually be very useful then. It wouldn't stick together as well, and that's why you wouldn't want to pick up a big stack of paper on the side. It just start falling out because everything can slide so easily. So what we do in heat treatment is we introduce these grains, and so these grains are imperfections. Now they can't slide past each other. There's no straight flat surface, and so that can alter the strength of our steel. So to get a bit more specific in what we're actually altering, heat treatment alters the number one, hardness, and the hardness is how strongly the metal resists the changes in shape. So can you bend this metal into a new shape, or is it very, very, very difficult to make it change shape? Toughness is related to how much energy it can absorb before breaking. So often if you have something that is really, really hard, if you hit it, it will shatter. And that's because something that's very, very hard is not tough. So for example, toughness, we can often describe as brittle. A brittle metal is something that is very hard, but it's not tough. In other words, it will break if you hit it. As hardness increases, you should know that toughness decreases. They have an inverse relationship. Ductility is the third one that we're changing, and that's the ability for something to be drawn into a wire. Now that we've cleared up these words, now we can actually look at the actual heat treatment itself. So I'm going to bring up another slide here. So there are three processes we use. The first one is called quenching, and you can see that in the introductory video. This is basically, we use the highest heat. It's sort of the first step of heat treatment after we've created something, if we want to create metal that's harder. So we heat it and then we cool it quickly in water or oil. And so what that looks like is something like this. We heat it up and then we submerge it. So it's going to cool down very quickly, and I'm highlighting quickly right there because we're going to compare it to the others later on. In water or oil, and sometimes we do it in oil if we're particularly worried about corrosion. So the reason we do this is the steel becomes harder through quenching. But the problem is it's brittle, it's not tough. So what happened there is it became harder. We've changed how the grains to make this steel harder. Now after that, it's hard but not tough. So that may have a good application in some things, but quite often we want something that is tougher. It can absorb energy without breaking. So then the metal will usually go into tempering. And so what we'll do is we'll heat it again, but now it's going to be cooled more slowly in the air. So here's the difference in how we cool it. Now the reason we do this is now the steel, the grains are changing again. It's becoming tough and springy. So we're increasing the toughness. It's becoming less hard, so it can change its shape. That's why it's springy now. So again, inverse relationship. More tough, less hardness. Reason two is that internal stresses. So for example, if there were some crystal structures that were sort of distorted or some gaps, micro scale gaps in the structures inside the metal, those internal stresses are removed through this process. And then reason three, it replaces the brittleness with toughness. And so that's actually another way of sort of restating almost reason one. But these are the three reasons they accept in the exam, so I would write all three of them. The last process is sort of a separate one. So we'd usually go through quenching, then tempering to make something that's harder and tougher. Annealing is what we're going to do if we want to make something softer. And if we're making something softer, it's actually making larger grains. And we're also making it more ductile, so we can draw it into a wire. So the difference in this is that we're actually going to heat this and keep it hot for several hours, and then cool it down very slowly, more slowly than tempering. So those are basically the highlighted differences of the different heat treatments of steel. And in the exams, they tend to address or ask about tempering a lot more often.